Okay, welcome everyone. Here's one of the videos where I'm going to try to work through and solve one of the puzzles that y'all have posted in and sent for me. So let's see how we go. Construct a natural deduction system for RM3. That is, construct a natural deduction system that proves all and only the arguments that have no RM3 matrix counterexample. And 2, demonstrate that this system does in fact prove all and only the arguments that have no RM3 matrix counterexample. Ooh, okay. Let me tell you right off the bat, I am unlikely to succeed at this. I mean, that's part of the fun is sort of seeing what it's like to dive in and bang your head off something when it's a bit of a challenge. But I'm going to kick off just by explaining a little bit more about what this puzzle is asking for. I mean, I'm sure those of you who posed the puzzle, of course, have a sense of what the puzzle is asking for, but I just want to make sure everyone sees what the puzzle really wants, and I'll give you a little bit of perspective on why that's going to be very difficult, and then I'll see what I can do. So, here we go. Okay, when we're thinking about connections here between model theories and proof theories, right, we've got this sort of logic, RM3, and as we've studied it, and I've drawn it behind my picture, which is not going to help you see anything. So let me bring that out from behind my picture. We're thinking about RM3, right? As we know it, it's been determined by a particular matrix, right? So we encountered it via a matrix. That's not of course, what the logic itself is. The logic is just a set of arguments. And so, in particular, this matrix that we looked at, this RM3 matrix, determines a set of arguments. Now, RM3 is not the matrix. RM3 is the set of arguments that that matrix determines. So it is possible that we could get at that same set of arguments in some other way. And that's what this puzzle is asking to do, right? It wants me to try to generate a natural deduction system, a proof system, like our NJ, NM, NK kind of proof systems. And a proof system itself, right, gets at a particular set of arguments. And so the idea here is to try to build a proof system that lines up with RM3, that gets at that very same set of arguments, but of course not doing it via a matrix, but instead doing it via a proof system. So in order to get a little bit clearer on how that works or what that might look like, let's think about sort of 2 different ways. If we have a sort of model theory or a matrix, let's even just zoom in particularly. Let's suppose we have a particular matrix and we have a particular proof system. And we want to find out, okay, do they determine the same set of arguments as each other or not? There are basically 2 ways for that to go wrong. And so in order to successfully complete this puzzle, what I'll need to do is make sure I don't make either of these mistakes, make sure I don't run into either of these problems. So what we want, right, is on the matrix side, we might have a counterexample to an argument that on the proof side, we also have a proof of. That would be one way for things to go wrong, right? Because if we have a counterexample on the matrix side, then sort of according to the matrix, according to the logic determined by the matrix, this argument is going to be invalid because it has a counterexample. But then if we have a proof on the proof side, then according to the proof system, this argument will be valid because it has a proof. So this would be one way for them to disagree, one way for them to not line up and determine the same logic would be, what if we have a counterexample and a proof of the same argument? That's one way things could go wrong. That's one thing that needs to be avoided. And when we do manage to avoid this, right, this is if we avoid this, that's what's called soundness. We'd say the proof theory is sound for the model theory. And what that means is they don't disagree with each other in this particular way. right? There's no argument that has both a counterexample and a proof. That is, a counterexample according to the matrix and a proof according to the proof system. And when there's no argument, where there's that kind of clash, where there's that kind of interference like that, then we say that the proof system is sound for the matrix. But there's another way that things might fail to disagree. We might have an argument where there's neither a counterexample nor a proof, right? So if there's no counterexample to it, then according to the matrix, the argument's going to count as valid. That's what it takes to be valid, according to a matrix, right? Is to have no counterexample in that matrix. But if there's also no proof to it, then according to the proof system, that argument's going to be invalid, because that's what it is to be invalid, according to a proof system, is to not have a proof. So this would be another way the matrix and the proof system could disagree with each other, could determine different logics, would be if we had an argument where it had neither a counterexample nor a proof. So this is another possibility we need to worry about. So what if we have an argument with no counterexample and no proof? Right? This would be a different way for things to go wrong. And if we avoid this, that's what's called completeness. So this puzzle is asking me to generate a proof system, a natural deduction system for RM3 that is both sound and complete, right? So a proof system where we never have a proof to anything with a counterexample, that's soundness, and a proof system where we always have a proof to everything without a counterexample, that's completeness. And in order to determine the very same logic, we've got to do both of these, right? Both of these have to line up. So this, for example, is the kind of relationship that we do have between the proof system nk on the one hand and our classical matrix on the other. If you remember the sort of Boolean structure with just that value t designated, right? That'll give us classical logic, and nk will also give us classical logic. So those do agree. That gives us an example where this does obtain, where we do have both soundness and completeness. For a proof system for a particular logic. But of course, in general, if you just like pick a proof system at random and you pick a matrix at random, this probably isn't going to happen, right? You need to set things up in a particular way in order to really have any hope of having this happen. Okay, now back up just a little bit. Again, this is just sort of giving you some perspective of why this isn't likely to go terribly well before I dive in and see what I can do. If you think about that relationship between NK and classical logic, right? We haven't, in any of the reasoning, in any of the readings, I haven't gone through, I haven't explained why that obtains, I haven't sort of showed you the details of why that's so. I've just sort of said, hey, it does, it's true that NK gives you exactly the same logic that the classical matrix does. And it is true. I mean, I'm not misleading you, I'm not lying to you here. But the reason that we haven't gone through that reasoning in some detail basically it's rough going. Thinking about these issues of soundness and completeness, or actually soundness, as we'll see in a moment, soundness is not that bad. Completeness is the hard one. Thinking about the details of completeness and thinking about going through what it takes to show that something is complete is definitely considerably more advanced than anything we're touching on in this unit. It would be, I think, a natural topic really for something like a second unit in logic to cover if there were any such thing at Monash, or if there is any such thing at Monash in the future. Something like completeness would be a natural sort of next stop to go to. But it's rough going. Completeness proofs can be quite difficult. And often when people develop a new completeness proof, or they develop a proof system and show that it is both sound and complete, but as I say, completeness is the hard part. That usually is the kind of thing that you can publish in a professional journal. It's a significant achievement. It's something that takes sort of real work and real challenge to do. And so it's almost certainly not something that I'm going to be able to just do off the top of my head in terms of thinking about this kind of puzzle. So that's just a heads up. As I say, soundness, not so bad. Completeness, real challenge, and I'm unlikely to be able to get there in this video. So that's it. Let's dive in. Let's start to think about RM3, and let's think about how RM3 might come together and work. So first thing to do if we're thinking about building our natural deduction system, one thing we want in place, would be nice to have in place, right, would be, can we have our good old ability to assume things? Can we just handle assumptions the same way that we do in things like NM and J and K? And in this case, yes, right? So the rule of assumption, or our ability to assume things, right, means that we always have a proof of argument from phi to phi, right? For any sentence phi, we can always prove that. We just assume it. That assumption is a proof, right? It has the open assumption phi, the conclusion phi, so there we go. So if we were dealing with a logic that wasn't reflexive, then we would have to start messing with our rule of assumption. We have to do something here. But RM3 is reflexive, right? RM3 is a matrix logic. Matrix logics are always reflexive. So we're covered on that front. So excellent. We can leave assumption alone. We've got our rule of assumption, right? Okay. Now let's pause here. Imagine a proof system where all we can do is assumption, where there's no other rules of any sort, right? Just assumption. That's it. So we always have this proof, phi or a phi for any sentence phi. But in a proof system like this, we wouldn't have any other proofs, right? All we can do is assume something and then stop. There's no way to combine proofs, there's no way to extend proofs, there's no way to do anything else. We just assume them. So we can assume something, we get this proof of phi or a phi. Sorry, from not phi arrow phi, but a proof with premise phi and conclusion phi. And that's it, and then we're done. We would also have in this system, right, proofs of really any argument. We could add more premises, because remember, you can always have premises that don't, in fact, occur as open assumptions. So we'd get proofs of more arguments than just these reflexivity phi to phi things. We get proofs of any argument where its conclusion is among its premises, even if it has more premises than that. Again, though, right, that's always true for any matrix consequence relation, so it's true for RM3. So in this case, we're still good. We're still on that front. Okay, now where are we at? Well, we know in this hypothetical system where all we can do is assume things, if we have a proof of something, then it's one of these things, right? It's an argument with its conclusion among its premises. So if we have a proof of anything, it's one of these things. And we know there are no counterexamples to any of these things in any matrix, and so in particular, no counterexamples to any of these things in the RM3 matrix. So what that means is that this proof system, the one where we just assume things and can't do anything else, is sound for RM3. It's sound for any matrix logic, and so it's sound for RM3 in particular. That's the kind of thing I mean when I say soundness is easy and the completeness is the hard part, right? So the way that I want to try to come at this problem is I'll start, say, with this proof system where we just assume things and do nothing else. So that's a sound proof system. And what I'm going to try to do now, it's not complete at all, though, like definitely not complete. So for example, right, RM3 has, this is valid, right? The argument, no premises, and P implies P is its conclusion. That's valid in RM3. There's no counterexample to that in the RM3 matrix. But there's no proof of it in this system where all we can do is assume things. Because in a system where all we can do is assume things, there's no proof of anything with no premises. Because we always have some assumptions open, right? We don't have anything that allows us to discharge assumptions if all we can do is make them. So in RM3, that's a 3. So in RM3, this is valid, but it has no proof. So no counterexample, no proof. So what we have here, this sort of very basic, bare proof system where we can assume things but not do anything else, this is sound but not complete for RM3. And so what I'm going to try to do is beef it up, add more proofs to it by adding more rules, enabling us to make more proofs. And each rule we want to make sure doesn't mess with the soundness. We want to keep the soundness in place and sort of get closer and closer to completeness in that way. That's the basic idea behind how this works, or behind how you would typically go about trying to build a proof system to do something like this. So let's think about some rules that we can add on for RM3 to get a hang of that and see how far I can get. Okay, so First thing we might want to think about with something like RM3. So probably want to come at it kind of connectivity by connectivity. I don't want this to go on forever, so I won't necessarily think through each connective in a massive amount of detail. But let's start with conjunction. Conjunction is almost always the easiest place to start. So let's not make things any more something than they already are. And let's kick off with conjunction. So when I think about, the first thing I'm going to want to do, right, is look at the sort of rules that we have for conjunction and say, well, can we just carry those over? Are those enough? Do they work? Can I have them without interfering with soundness? And do I need more? Or am I likely to need more to achieve some kind of completeness or not? I don't know. So let's think on the one hand about how conjunction works in RM3, right? So we've got T star and F and T star and F, and conjunction in RM3, right? The structure we're looking at, except for implication, all the other connectives, we're basically looking at the strong Claney structure. So conjunction is going to work just like it does in the strong Claney structure. And then our designated values in RM3, right? These are the designated values are the T and star. That's what we're looking at. So with that in mind, let's think about a rule like our conjunction introduction rule. And let's think, can we have that kind of rule? If we added that kind of rule to a proof system for RM3, or a candidate proof system for RM3, would we be interfering with soundness? Right, so we suppose we have some proof system for RM3 that is at least sound, not necessarily yet complete. If you want one of those, just think about our assumption-only proof system, right? That's sound but not yet complete. So okay, suppose I had some proof system that's sound but not yet complete. Can I add this rule to it? And will the resulting proof system still be sound? Let's think about that. Okay, well, what does this rule really say, right? It looks like that in schematic form. But what it really is saying is like, look, if I have a proof up here somewhere, and I also have a proof up here somewhere, then I can put those together and get this kind of new, larger proof that contains them all, but has this new conclusion. And now I want to take that kind of thought about proofiness and translate it into a thought about validity of arguments, right? Because we've got matrices on the one side, proofs on the other, and the only way to go between them is by thinking about arguments, right? It's arguments that sort of occupy that middle ground and do the connecting here. So if I'm thinking about this rule, I'm just going to move it to a more convenient place for thinking about it. So if I'm thinking about this sort of rule, here's a way to think about it, right? Is I think, okay, well, if there's a proof of some premises to phi, and there's a proof of some maybe other premises to psi, right? These are the two proofs coming in. Proof of that. Then, what this rule gives us is a proof of that, right? So we throw all the premises into one big pile. Why? Well, because in this rule, we throw all the open assumptions into one big pile, and the conclusion comes out to be the conjunctions. So now here's a question that I want to ask. This rule is going to work if this is true of RM3, but instead of proof, I want to ask this question. Does this hold of RM3 validity? All right, I want to know, is this true? And if it is, then as long as my original proof system is sound, then I can add this rule to it and I'll still maintain that soundness. right? Because any application I made of this rule would be one where, okay, indeed, anything I get a proof of coming out, as long as the things coming in, those were really valid, but then the thing coming out will really be valid too. So I want to ask, is this true of RM3? So, okay, now, so note this is stated entirely in terms of validity and arguments. There's nothing here about proofs, and there's nothing here about matrices, right? That's what enables it to be this sort of bridge. But now I want to read it back into the matrices and see, does this in fact hold? So, how to go about this? Probably the easiest way, I think, is sort of turn it around. Right, so rather than thinking about validity, I'm going to now think about invalidity. So I want to take this same idea that I'm wondering whether it's true and say, okay, well, I can express this same idea a different way, in a way that might be easier to tell whether it's true. And the different way I want to express it is thinking, okay, well, if what we really are asking is like, is it true that if this thing is invalid, then at least one of these must be invalid? And if that's true, that's the same thing that I'm asking about. So let's suppose that this thing down at the bottom with the conjunction as its conclusion is invalid. So that means we have some valuation, some strong plane evaluation, that gives designated value to all the premises, that an RM3 designated value, so either T or star, to all of the premises, everything in gamma, everything in delta, but also gives an undesignated value, and the only undesignated value here is F, gives an F to that conjunctive conclusion. And now I can come back and think about this and say, okay, well, suppose I do have a conjunction that receives the value F, right? So what that tells me, if I have a conjunction that receives the value F, is that I'm somewhere in there. And what you can see if the conjunction receives the value F is that one or the other conjunct has to take the value F. Right? If the conjunction gets the value F, then at least one of the conjuncts has to take the value F. And that's coming right from the table. That's coming right from how conjunction works in this structure. Is that if the conjunction as a whole takes the value F, then it must be that at least one conjunct takes the value F. So now we return to this question I'm asking. So if this thing at the bottom is invalid, right, then it has a counterexample. And let's think about what that counterexample must do to these top arguments, right? Whatever that counterexample is. I don't know what it is, right? I just know it's a counterexample to the bottom argument. Well, it gives everything in gamma and everything in delta a designated value. So for both of these top arguments, right, it gives all their premises designated values. And what we just found out checking the table is that if the conjunction is undesignated, it's value F, then at least one of the conjuncts is value F as well. So that means that this counterexample that we're assuming to the bottom one must itself be a counterexample to at least one of these top two ones. In other words, it's true that if the bottom thing is invalid, then at least one of the top two things is invalid. And that's the same thing as saying it's true that if both of the top things are valid, then the bottom thing is valid. So is this true? Yes. Yes, it is. And that means, now we're kind of stepping back to where we launched off of all of this, is that if we have a proof system that's sound for RM3, then adding this rule to it, the rule of conjunction introduction, will retain that soundness. Right? So, and we did in fact start out with a proof system that was sound for RM3, the rule of just assumption. So now here's a bigger proof system. Guarantee you it's still not complete, right? There's still no proof of P implies P. But it's better because now we can prove, so assumption plus conjunction introduction. Now we can prove things like, you know, P, Q to P and Q. Now we have a proof of that. And the assumption only system, we didn't have a proof of that yet. Now we do, we can prove it by conjunction introduction. So we're still sound. We're still not complete, but we're getting there. And it's these steps towards completeness. This is the kind of path of building up a proof system. So I went through the reasoning about that particular rule in some kind of repetitive or laborious detail. But each step of the reasoning is relatively formulaic, and this is kind of why soundness proofs tend to be the kind of easier part. Completeness proofs are often less formulaic than that, or the formulas are more complicated anyway. So that gives us conjunction introduction. Let's think, again, I don't want to go through everything in horrific detail. I want to get to the bit where I'm kind of out of my depth and flailing pretty soon, but I want to give you one more example of at least the kind of thing I want to try to do. Right, so let's think about conjunction elimination on the right, for example, and think, okay, can we add this rule to RM3? Can we get that in there? I don't know why that keeps happening. The sort of expandy color thing from the top. And it seems to happen even when I'm not touching the screen, but oh well, okay. So, suppose we have a soundproof system for RM3, can we add this rule to it and retain soundness? Well, again, think about what this rule really means as we're building proofs, right? It means if we already have some proof here, then we can extend it by a step into this larger proof, which will have the same open assumptions, but a different conclusion. So this is really telling us, right, if there's a proof of some premises with the conclusion phi and psi, then there's a proof of those same premises with the conclusion psi. And to know whether we can carry that forward again, now we want to ask, okay, that's what this rule says about proofs. Is this true of RM3 validity? Right? Is it true that if this thing is valid, then that thing is valid? And again, we're going to want to answer this question as we go back to the matrix by flipping this around, right? So this is now our question. It's like, is this true? This claim. Let me just move it a bit. And again, we're going to want to flip this around and say, okay, what we're going to ask is it true that if this is invalid, then this is invalid? Right? Can we, asking about passing validity from top to bottom is the same as asking about passing invalidity from bottom to top. So suppose that bottom one is invalid, right? Suppose we have some counterexample. Well, that has to make all the premises designated, it has to make everything in gamma designated, and it has to make psi undesignated. It has to make that conclusion undesignated. In particular, it means that it has to give that conclusion the value f, because that's our only undesignated value in RM3. Well, what is that valuation? That's a counterexample to the bottom one. What does it say about the top one? Well, we know it designates all the premises because it's the same premises, right? It's the same deal. And now we return up here to our table for conjunction and get rid of the blue line. So now what we know is we're dealing with a conjunction whose second conjunct, whose right conjunct or right component is undesignated. That is, it has the value f. So we know we're in this column. And since we're in that column, it doesn't matter what value the left conjunct has, you can see the whole conjunction will always have the value f, as long as we're in that column. So returning to our question here, is this true? If the bottom thing is invalid in RM3, then that means we have an RM3 counterexample to it. But in any valuation that's an RM3 counterexample to the bottom one, we've just seen is also a counterexample to the top one. So this is true, right? If the bottom one's invalid, then the top one is invalid. So if the top one is valid, then the bottom one is valid. So this is good too, so we can add on conjunction elimination into our proof system. And so we're building something up here. That reasoning, of course, was just for conjunction elimination on the right, but if we come back up here to this and we say, okay, well, what if we cared about the first conjunct instead? Well, again, it's all f's, and that'll give us conjunction elimination on the left. So now we're starting to get rolling, building up a more involved proof system here. We've got conjunction introduction, both conjunction elimination rules, rule of assumption. This is all sound for RM3, not yet complete. Okay. Let me just pause there, catch my own breath, catch my thoughts a bit, because that's the part that's gone well. Now I want to get to the part that's not going to go as well. Or at least that I expect it's not going to go as well. And this is the part that starts to get a little bit what's maybe more distinctive about RM3. And that's the implication connective, right? That's the key sort of deal for RM3. What makes it kind of distinctive in its own beast is thinking about the implication connective. So I'm going to start again by just giving myself the table to refer to. And these are designated. And before I get too involved at banging away off of this, I'm just going to do a quick double check to make sure I've actually got that table right. For the earlier strong planing conjunction, I've worked with that enough, I'm sure I know it. This one, I do just want to double check to make sure I've got that table right before I waste a bunch of time doing some stuff about the wrong table. So I'll check that and be back in just a jiff. And all I'm doing now actually is just opening up EMU and setting it to RM3 and telling it to show the connective tables. And sure enough, I did get it right. Okay, so this is the table we're working with. So let's think about this. So one thing we know about RM3 from the reading we went through before is that it doesn't actually obey the deduction theorem, or I might have called it conditional proof. Sometimes it's called conditional proof, sometimes it's called the deduction theorem. I'm actually just going to pop open the notes so that I can take a look at, what did I call it? I called it conditional proof. And now I'm just zooming forward in the notes to get the counterexample to conditional proof. Here we go. So here's a counterexample to conditional proof in RM3, and this is just taken from the notes where RM3 is originally presented. So that is RM3 valid, but this is not. And this is the kind of thing that's going to start to cause some trouble here. Because if I think about the kinds of rules we have, so we want some rule to be able to prove some implication sentences, because as we've seen before, right, like this, just P implies P with no premises. That's valid. So we definitely need some rules in this proof system that are going to enable us to prove implications. And they're going to need to be able to discharge some premises, right? Because so far, all we can do is start, well, either discharge open assumptions or just work without any open assumptions straight off the bat. But we're not going to be able to use implication introduction. And the reason is this issue right here, not having conditional proof. Right? So if we had a system that was complete, if we really were there, then because this is RM3 valid, then there would have to be some proof of it. And indeed, we already have a proof of it, right? Just assume P, and that gives us a proof of this argument. But with implication introduction in hand, at least the implication introduction that we use in NJ and in M and in K, we can go from that to a proof of this. But since that's not valid, we really don't want to have a proof of it. If we have a proof of that, then we've lost soundness, and then our whole strategy of like holding to soundness and building up and building up and building up fails, right? If we go too far, we lose soundness, then our whole strategy is out the window. So that means implication introduction, at least of the kind that we know about so far, is not going to be legit, and not going to be something that works for RM3. So here's a guess that I have, and we'll see where it goes. I'm going to think about now, let's think about a modified implication introduction, where we say you must discharge at least one occurrence. Right, so our normal implication introduction, we allow you to discharge nothing at all. Indeed, that's how you would come up with this proof of the argument from P to Q arrow P. You would do that, right? You'd assume P. Then you would have an implication introduction where you discharge nothing, and you would introduce the Q arrow P. And that's the kind of thing, this is the kind of thing we don't want, because that's going to violate soundness for RM3. So if we want to get rid of that, one way we can get rid of that particular proof anyway, is saying, okay, we want to get rid of this where you must discharge at least one occurrence. So that gets rid of this particular example. I genuinely don't know whether this modified one is sound for RM3 or not. So let's think through that and see how that goes. I'm aware of the amount of time this video is taking, so I might start to break it down after that. But let's think about whether or not this modified rule is sound. So, okay, what does this modified rule really say? It says, okay, if there's a proof of something like this, where that phi really occurs as an open assumption, then there's a proof of this. And now I think you can start to see here to some extent how the earlier strategy of trying to prove soundness is actually going to break down a little bit here. Why is that? Well, the earlier thing was just, we moved at this stage from thinking about proofs to thinking about validity, thinking about which arguments are valid, and that was sort of how we were passing our way over to getting to the matrix and being able to think about the matrix. But in this case, this sort of extra restriction on having that really is an open assumption in the proof, that has no counterpart when we think about validity, right? What is or isn't actually an open assumption in the proof is just a matter for the proof, as far as we've handled it. It doesn't have anything to do with what happens as we pass it over to validity. So there's definitely going to be a blip at this stage in terms of trying to just sort of formulaically follow the earlier approach. And I'm not sure that off the top of my head I see a great way around that. So I don't know whether this modified implication introduction is or isn't sound. I kind of bet that it is, but that's not based on much. That's not based on much, and I don't see off the top of my head a way to go through particular reasoning to demonstrate that. Let me give you a different kind of way we might come at something like this, a different sort of approach. Rather than taking a rule that we know is unsound, like the normal implication introduction, and then trying to restrict it back to get it baked under soundness, because those restrictions might be difficult to work with, as we've seen in this case. It's a different kind of approach that we could take, and this is more like the approach that NK takes. So you remember in NK, we just have this rule that just from out of nowhere lets you prove an excluded middle. We could try bringing in rules like that, right? These are something more like our old axiomatic proof systems, where we just sort of whack some things in out of nowhere and say, well, these are free, you get proofs of these without any issue. So all we would need to do for that is make sure that the things we're allowing proofs of really are valid in RM3 so that we get soundness. So for example, we could imagine having a rule that just lets us do that, just put in phi or phi, and that would, well, it's certainly sound, right? That's a valid, the argument no premises in that as its conclusion is valid in RM3. So that's good. We could probably do some other things like and again, just say we have that from nothing. I'm pretty sure that that's a theorem of RM3. So let's think about it. How could we get that to take the value f? Well, what would we need to do? Well, we would need to give its antecedent either a t or a star, and then we would need to give its consequent some lower value than whatever value we give its antecedent. So if we give its antecedent either a t or a star, that's this phi here, then can we get the consequent here to have a lower value? So suppose we give this thing a t, so can we get this embedded implication, can we get that either to a star or to an f? Well, we've just said what it would take to get it to an f. What would it take to get it to a star? That would be to give its antecedent either a t or a star, and its consequent either an f or a star. That would get it to a star. So what if we give psi star, and now we're forced to t and star, so that is itself star. So now we have star arrow star, which is star, and that gives us t arrow star, which is f. Okay, so this is not a theorem of RM3. I was mistaken, right? Because here's a valuation that gives us a counterexample to this. If I did that right, and so t here, so t and star is star, and star arrow star is indeed star, and t arrow star is indeed f. Yeah, so this is not a theorem of RM3, so we definitely don't want to add this rule in, because that would not be sound. But we could add in rules, other sorts of rules that would get us things like that. So that should certainly be a theorem, and correspondingly for the other component of the disjunction. So again, we start building up those sorts of ways. So let me zoom out a little bit and give a sense of what's going on. If I'm thinking about building a proof system for RM3, this is the general strategy I'm going to try to take and come at it with, right? I'm going to start from things I know are sound, and I'm going to expand by putting in more things that I can show are sound as we go. And I'm going to try to get it out until basically until it feels like there's some shot at it being complete. Then the work is in actually seeing whether it's complete, showing that it's complete. And this is, there's a few different ways that people attempt to do this, and there's no way I'm going to go through this in detail. Like I said, this is considerably more advanced than anything we're touching on in this unit. But I want to give just a general flavor of the strategy that people would take to do that. So at least one standard way to show completeness is you show a strategy, you show a method, you show, give a method that starts with any argument now we can do even better. Now let's go with a slightly different kind of method. It might be easier to understand. So give a method that starts down, big brushes, starts with any unprovable argument. Right. So we've got some proof system. We want to show that it is complete, which is to say every argument has either a proof or a counterexample. So the way we show that is we give a method that starts with any unprovable arguments. We know this doesn't have a proof. And so we want to show that it does have a counterexample. That's what will get us to completeness. And then the idea is that we want to like build up a counterexample to that argument. And at every step of the way, as we build up a counterexample to that argument, we're going to be leaning on our knowledge that it's not provable. Right? So we suppose at the outset that it's not provable. If it's provable, we're all set, because completeness just means everything either has a proof or a counterexample. So if it has a proof, we're all set. What we really care about are cases where it doesn't have a proof. And one of the standard ways to build up a counterexample to that argument, so think about something like, here's an argument that we saw was not valid in RM3. So if you can imagine imagine we have some proof system that maybe is complete for RM3 and maybe isn't, and we're trying to do this completeness method to show that it isn't. What we would do is take an argument like this, and we'd say, okay, well, here's one thing that we would know about this sort of thing, right? Is if we want to build up a counterexample to this argument, we need to give this thing the value f. because that's the only undesignated value. Conclusion has to take an undesignated value in a counterexample. And then we would say things like, okay, well, where can the conclusion get a value, or where can the consequent of an implication, how does an implication itself get the value f? Well, it gets the value f in these sort of spots. So that narrows down the possibilities for what we could be looking for, right? We're either looking at T arrow star or at T arrow f or at star arrow f. Those are the only possibilities. So as we're trying to build this thing up into a counterexample, then we say, okay, well, we're either looking at T arrow star or at star arrow f or at T arrow f. Those are the three possibilities. And then we look over here on the left and we say, okay, well, we need the premise to be designated. So in this case, that star will do, and these other ones won't. So that gives us our counterexample in this case. The difficulty and why this is such a challenge is what you need is some way that you know will always work no matter what unprovable argument you start with, right? So I just did a little bit of a search there. It did in fact happen to work, but that's just one example. That shouldn't reassure us that that method will always work. And the trick to building the method that always works, right, is we've got this word unprovable and we get to assume that the argument is unprovable in showing this. But we also got to build the proof system in the first place, right? Remember, this is some proof system that we built. So you kind of squeeze at the method from that, right? You build up the proof system that sort of gives you the structure that you want. And then the way you're going to use that structure is by spelling out a method that tells you how to take for any argument that you can't prove, how you can generate a counterexample to that argument. That's at least one standard way that someone would go about showing completeness. And if that sounds difficult and complex, it is. It's the nature of the beast. A completeness proof written out in full, even written for experts without a lot of discursive hand-holding and so on, but that just goes actually through the details, can be 4 to 6 or 7 pages of just like symbols and cases, and it gets pretty hairy over here, and it definitely is not the kind of thing that I can do off the top of my head. So anyway, I hope this gives you some sort of sense of what would be involved in solving this kind of puzzle. As I say, this turned out to be a very difficult puzzle about RM3. I'm going to go ahead and pop this puzzle itself up on the forum as an unsolved puzzle, so that we can all have a crack at it together and sort of see how far we can get and can we pull it off. I don't necessarily expect that anyone's going to pull out a completeness proof for anything, but be nice even if we can get to a proof system that we think has a decent shot at being complete. We'll see where we go with that. But I'm going to stop this recording now for this puzzle so that I can move on and check out some of the others. So there we go.